Okay, so I want to continue talking about propositional logic or symbolic logic. Again, you hear it called both, as I said in last lecture, and I really don't care which of the terms you use. I don't really think it's important. I'm just going to call it propositional logic because, well, I think that might be a little more common than symbolic logic, but whatever. All right, so remember I said last time, the basic idea is every simple proposition, you give a letter, that stands for the proposition. More complex sentences, you assign letters to all the propositions, then you figure out how they fit together, And is one symbol, or is another, not is another. Now there's some stuff here that we're not going to cover. There's conditional statements, if, then. Those are really, really tricky. We don't really need it to do the stuff I want to do with inductive logic, so I'm not going to talk about it. All right. So anyway, you can use symbols to represent much more complex propositions, much more complex sentences than we were talking about last time, right? So here's one. I'll take either French or Spanish next semester. I might even take both, but I definitely won't take German. I will take French, R. I will take Spanish, S. I will take German, G. So you have R or S and not G, right? R and S connected by the little wedge or V symbol. And then you have this not G. Now, one thing to notice, like the book talks about the main connective, that's the one that determines, the truth value of this whole big block of letters, right? So your book talks about the main connective, or you might say main symbol. That's the one you look at to see if the whole statement is true or false. Here, the main one is this and, this little ampersand symbol, right? Here a couple more. In this not A or B, the main connective is the little tilde sign, the little not symbol. And in not A and not B, it's the and, right? Now look, how do you read these? How do you create these? Well, one thing to do is to treat everything inside parentheses as one letter. You always want to do that. So like when you go back to this one, how do you read this one? Well, you start with this R or S. You read all this stuff in parentheses as one letter. You want to look, well, are either R or S true? If they are, then all the stuff in the parentheses, you can just fill it in with a T. Then you look, well, that this not G, right? Now, I'll talk a bit more about how we read this sort of logical notation, how we symbolize stuff. This is actually something we're going to spend a lot of time on. We're going to spend at least a whole class session practicing it. Because especially for reasons that I'll get into, when you get long strings of stuff, when you get more complex sentences, this can actually be a little tricky. So I think it's something, that's worth practicing. But I want to talk about a few other concepts in the lecture today. Then the next lecture we'll come back to some more stuff about how to read this logical notation, how to symbolize longer sentences. So the first thing I want to talk about is logical entailment. Weisberg talks about this. I think he gives a decent explanation, but it's worth going through again. Maybe you look at it a different way. So logical entailment means, statement 1 logically entails 2. What that means is whenever statement 1 is true, 2 is true as well. Here's some examples. A and B logically entails A. Whenever A and B is true, A will also be true. A and B logically entails A or B. Whenever A and B is true, remember we're using this inclusive or, A or B will be true as well. If you want to prove this, I think, probably if you think about it, it'll make sense to you, but, logic is all about proving, not just what seems to make sense. the truth tables that we've looked at give you a way to do this, right? So, if A and B logically entails A or B, well, whenever A and B is true, A or B will be true as well, right? Well, there's only one line here, the top one, where A and B is true, and lo and behold, A or B is true on that line too, right? I also said it logically entailed A. Well, that means whenever A and B is true, A will be true as well. Well, again, there's only one line where A and B is true. On that line, A is true as well, right? Now look, logical entailment, it's good to keep in mind, it doesn't run both ways, right? A and B logically entails A or B means that whenever A and B is true, A or B is true. But it doesn't mean whenever A or B is true that A and B is true, right? Look at all these lines here where A or B is true. Line 2 and 3, where A and B is not, right? And again, there's at least one line where A is true and A and B is not, right? Line 3. So, whenever, logical entailment, whenever you have the statement A and B, you also have A or B, but not vice versa. You also have A, but again, not vice versa. Now, when you have this vice versa, when one is true, the other is, and when the other is, when they go both ways, that's logical equivalence. Logical equivalence means statement 1 and statement 2 are logically equivalent when they always have the same truth value. And, whenever 1 is true, 2 is true too, and vice versa, right? Logically equivalent, 1 is true, then 2 is also true. 1 is false, 2 is also false, and you can reverse it, right? That's the important difference between logical entailment and logical equivalence. In this case, whenever 2 is true, 1 is true. Whenever 2 is false, 1 is also false, right? So here's an example your book uses. Pretty simple one. A or B is logically equivalent. A and B is logically equivalent to B and A. A and B means the same thing as B and A for purposes of logic. Look. On lines 2 through 4, A and B is false, B and A is also false. On line 1, A and B is true, B and A is also true. These two statements have the same truth value. On every single line, that means they're logically equivalent. And for purposes of logic, what a statement means is just, it's when it's true and false. A and B means exactly the same thing for purposes of logic as B and A. Here's another example. Not A and not B is logically equivalent to not A or B. So why is this? Remember, think of it this way, right? We have this not symbol, it sort of flips the value of this, so the not A is only true when A is false, not B is only true when B is false, the and is only true when both of these come out to be true. So it has to be the case that both A and B are false for not A and not B to be true. Well, remember, we read everything inside the parentheses as sort of one letter. Whenever A or B is true, the stuff inside the parentheses is true, but because there's a not, whenever it's true, the not is false, right? That's the thing you look at. So the only way either of these is true is when A and B are both false. Or again, let's look at the truth table. There's one line, the first three lines, both not A and not B are false. And the final line, they're both true. On every line of our truth table, these two formulas have the same truth value. Whenever one's false, the other one's false. Whenever one's true, the other one's true. The only line where they're both true is line 4. These two statements are logically equivalent. You don't need to memorize what statements are logically equivalent. You just need to understand how this works, how it's defined. One more example, not A or not B is equivalent to not A, not A and B, right? Again, when you think about this, all that needs to be the case for not A or not B to be true is that either A or B are false. All that needs to be the case that not A and B is true is that one of them is false, right? Because remember, well, anytime one of these is false, we're going to read this stuff inside the parentheses as false, but the little negative negation symbol flips it, so we get a true, right? Line 1, they're both false. Every other line, they're true. They have the same truth value on every line. They're logically equivalent. I know this can be a little complicated. This is already getting very abstract, but it's really not that complex. It's not that hard when you take a step back and think about it. I know when things get abstract, they seem confusing, but the basic ideas here, not anything too complicated, I don't think. Once you get to this level of abstraction with these symbols, you can almost treat this like a game. That's one way to approach these.